Okay, and so now we're at the last talk of the session with Yixuan Li, who's going to present his work on guided tensor lifting.
Hello everyone, welcome to my talk. This is the last talk of the day. My talk is about guided tensor lifting. My co-authors are José, Wesley, the Souza Magalhães, Alexander Brauckmann, Michael Boyle, and Elizabeth Polgreen. First, let me introduce you to program lifting. Previously, all code worked on all hardwares. And if the hardware got faster, your code got faster automatically. Hardware is now becoming more specialized with corresponding DSLs. TPU, GPU, AI accelerators, they all ship with their own DSLs. And using this specialized hardware gives performance gains. In machine learning worlds, machine learning workloads are dominated by tensor code. And the key to efficiency is the highly parallelized algebra. DSLs like Taco make this easy for new applications. Taco is the tensor algebra compiler, a fast and versatile compiler-based library for sparse linear and tensor algebra. Okay, we can now write our new applications with new DSLs, but what about the legacy code? Do we need to manually lift C to Taco or PyTorch or NumPy, or manually rewrite MLR to JAX, or manually lift C++ to Halide? Do we need to do that? That's painful for millions of lines of legacy code, right? So can we automate the process of language lifting so we can just lay down and play our mobile phone? We're focusing on lifting C code to Taco code, but there are lots of other DSLs that this work could apply to. First, let's look at an example. This is a legacy C code. What it's doing, it is doing a dot production. That one. And the corresponding Taco expression in Einstein notation is AI equals to Bij times Cj. Taco expression can then be compiled to highly parallelized dense algebra. The Taco speedup for our benchmarks will be 1.79 times on the multi-core platform and 24.1 times faster on the GPU compared to the previous legacy C code. What can we do for the automated program lifting? Maybe we can use program synthesis. Program synthesis is the task that automatically finds a program which satisfies a specification. And here in tensor lifting, specification is the legacy C code. And the grammar to guide the lifting is the Taco grammar. But we are facing problems. This is the Taco grammar, part of the Taco grammar. It is long. And search space grows exponentially as the programs get longer. Thus, the synthesis time grows to infeasible levels. So what shall we do? Maybe, try LLM. LLM code generation is fast and scale with program complexity. But it also has a problem. What is that? Hallucination, right? So there will be two questions. What if LLMs produce plausible-looking yet fundamentally flawed solutions? Maybe you try again. We sample 10 times. And how can we still use LLMs despite hallucinations? We treat LLMs as tools for ideas, not guarantees. That is our chance. So the answer for those two questions is we can combine LLM with an enumerative search from program synthesis. So our pipeline will be something like get solutions from LLM and generate probabilistic grammar. Then we guide enumerative synthesis with the probabilistic grammar. This is the figure of our pipeline. We can split it into 4 parts. LLM part, guidance, search, and verification. Let's go to our first part, LLM part. If we have an input C program, we can prompt our LLM to get 10 possible solutions. This is our prompt. We say, you are a scientific assistant that knows a lot about transpilation. Translate the following C code to an expression in the Taco tensor index notation. The expression must be valid as input to the Taco compiler. Return the list with 10 possible expressions. Return the list and only the list, no explanations, followed by the input C program. And we will get something from LLM like this. This is the response. Now let's move on to our second part, the guidance. Actually, there are two small parts in the guidance. One is the probabilistic grammar on the top. We need that to generate the right-hand side of our tensor probabilistic grammar. And another on the bottom is the dimensional analysis. We need it to generate the left-hand side dimension. Why do we need two parts? Because LLM, it doesn't know the left-hand side. We tried it. It just doesn't work. So we need two parts, one for the right-hand side and another for the left-hand side. Let's go back to our example. For the left-hand side, we need to determine this one, AI. So how do we determine the left-hand side tensor? First, we look for main assignment. What are the main assignment for this input example? These three lines, they are the main assignments because only PT increases in those for loops. And PT is initialized to result. Then we count the number of loops controlling pointer increment, which is the PT. We just find PT, these two lines. That is a single loop. So we can say it represents a 1D array. Thus, we can rewrite our left-hand side from int star result to AI. Now let's move on. If we have a result like this, actually, line 1 and line 3, they're identical if we normalize it to the middle one. Actually, the middle AST, the middle tree. AI equals to BJI times CJ. And according to guided enumerative program synthesis with large language models, our previous paper accepted at CAV 2024, we can extract a probabilistic grammar from the LLM's response. But using a grammar of templates is different from the CAV work. Convert a set of LLM-generated tensor expressions into a grammar that captures the likely space of the correct solutions. And the frequency of each pattern in LLM solutions indicate its likelihood of being correct. This is the grammar for all ISM expressions. And this is the grammar for ISM templates with holes. What we need is to fill those holes with probabilistic grammar. If our response is something like this, we can have a probabilistic grammar like this one. The line 2, tensor 1 defines as AI, and the probability with 1 is from left-hand side, the dimensional analysis. And the rest of them, line 3, line 4, and line 5, that the right-hand side comes from LLM solutions. Okay, now we have finished the guidance part. Let's go to our search part. If we add the search engine here, we can finally have a pipeline that looks something. We can get a candidate. In our search engine, we're using A* enumeration. It chooses paths based on minimizing path score. And the score is the cost so far, plus the estimate of cost to complete the program. And the costs are calculated from the probability. Let's have a very easy example. If this is our grammar, we first initialize the queue with the start symbol E. And here's the queue stores partial programs with scores. We have E, and we pop the partial program from the queue with the best score, which is, now it is E. We pop it, and then we expand it. We can expand it to T and E plus E. We update the queue. It is updating. And we pop the partial program from the queue with the best score. E plus E can be expanded to E plus E plus E and T plus E. Then we update the queue. It is updating now, yeah. And the highest score partial program should be T. We pop it, and we expand it to A and B. Now we update the queue again, and we pop the partial program with the best score, which is A, but actually A is not a partial program, it is a complete program. So now we have a candidate. We can verify it. Before verifying it, let me introduce our two different enumerators. The first one is the top-down enumerator. If this is the LLM response, we can use the top-down grammar to guide the top-down enumerator. The top-down grammar looks like this. Top-down enumerator expands from the root symbol downward, and it naturally handles nested or deep expressions. The estimate cost at node X is the minimal additional cost required to complete the partial expression to a full expression. And another is the bottom-up enumerator. This is the grammar to guide the bottom-up enumerator. It builds expressions from smaller sub-expressions upward, and it finds short expressions quickly. The estimate cost at node X is the minimal additional cost required to build an expression with the predicted length. And the length, it comes from the solution, the LLM solutions. Okay, now let's go to the final part, verification. It contains two steps. The first one is validation step. If the candidates succeed, we can move to the second step, the bounded model checking step. For the validation step, it is an IO check. It checks if a synthesized Taco expression can produce a program equivalent to the original C code based on input-output behavior. The process is like we generate IO examples. We run the original C code on random inputs to get expected outputs. And then we instantiate the Taco expression. We try all valid substitutions of the tensor and constant symbols. Then we run each instantiation on the inputs. We only accept Taco candidates if output match. Then we go to the bounded model checking step. It proves that two programs are equivalent up to a bound. The process is we lower both programs to MLIR, both the C, the original C, and the generated Taco. The Taco expressions, it uses JAX plus NumPy to emit MLIR. And then we compile them to C with assertions. We assert equality of outputs for all inputs up to a bound. And for the bounded model checking, we use CBMC plus CVC5 to verify the assertion holds. These are our benchmarks. We have linear algebra benchmarks, machine learning, image processing, signal processing, math functions, array programming, and we also contains 10 artificial, which we made it ourselves. Here are our baselines. The first is the previous state-of-the-art C2 Taco. It is a synthesis tool that generates Taco code from IO examples. It implements a bottom-up enumerative algorithm without guidance. And another baseline is also a previous state-of-the-art synthesizer, Tenspiler. It uses intermediate language, TensIR, that expresses tensor operations. And TensIR enables lifting, verification, and code generation. Okay, let's look at our results. For the percentage of coverage, the LLM, it can solve 44% of benchmarks, and the previous state-of-the-art, they solve 78 and 87. The best is our top-down enumerator. It solves 99% of benchmarks. And yeah, we win. And for the synthesis speed, let's set C2TACO as baseline. TensorPilot is 5 times faster than C2TACO. Top-down is 7 times faster than C2TACO. And the fastest is bottom-up. It is 12 times faster than C2TACO. Double win. And this is my talk. I'm on job market. Here are part of my first author papers. If you need to find an expert in LLMs and code generation, code lifting, please go find me. I'm on job market. My name is Yixuan from the University of Edinburgh. Thank you very much.
Thank you for the talk. So we have 3 or 4 minutes for questions. I imagine there are a lot of them. Okay, one question.
Thanks for the great talk. So can I know the benefit of top-down method compared to bottom-up? Because as far as I remember, the top-down method is a little better than bottom-up method.
So your question is about why top-down is better than bottom-up, right?
Exactly.
Yeah, because our benchmarks contains nested expressions, which means there are parentheses, like A plus B with a parenthesis and then times C. But a bottom-up enumerator, it cannot build such expressions because it built from smaller expressions and merge them together. It cannot do that. That is why top-down is better than bottom-up. And maybe if you ask about the synthesis speed, because bottom-up, it searches from smaller expressions and then to the longer, so it will find the expression, the solution first, because the solution might be smaller.
Another question. Yep.
Thanks for the great talk.
Thank you.
I want to hear about the other, a more complex example, because the Einstein sum, that was the example of the talk, but it was pretty simple that I think that just LLM can solve the problem. So do you have any good example that can show the effectiveness of this approach to solve some more complex expression that TACO can express?
Okay, if you want to solve more complex expression, you can find our previous paper, CAV'24. That is more complex than this one. You can go read that paper.
Okay. Yep, in the back over there, there's a question.
Yeah, thanks. Maybe a bit as a follow-up to that.
Yeah.
So you had 99% in the top-down. Can you talk about the 1% that you couldn't solve? Like, is there an example of one that you couldn't?
Oh, that one is the hardest. It is long, and our timeout is set as at 1 hour. If we extend it to 2 hours, we can solve it.
Okay. Let's thank our speaker one last time. Bye-bye. So that's the conclusion of today's session. I think, yep, we're done for the day. There's some more events in the evening, so feel free to enjoy the rest of the day.